Hello and welcome. Today we're going to be talking about residues at infinity. So recall from before, we had what's the residue theorem. And the residue theorem stated that if I have some contour, a simple closed contour that's positively oriented, and I want to compute f of z dz on that contour, an integral of that. So again, I'll write that a little drawing here. And suppose that, we're going to assume that f has finitely many singular points, like that. And here's my contour then. Then what I'm looking for is if, I look for the set of zk that are inside the contour C, and these are the singular points. Then what I can do is actually write this integral then will be equal to 2 pi I times the sum so k equals 1 to n, k equals 1 to n of the residue of f at z equals zk. Okay. So this gives us a nice way of breaking down an integral of some closed contour into just studying how many singularities and the relationship the singularities have to each other. And we have to just compute the residues then at each of these individual contours and just add them up. So essentially this can be a time saver. Okay, the question then is, of course, it's a time saver, and I should say, I put in a big star there, unless there are many singularities. Another question then is, what if I actually have a contour? So another question then is, what if the contour encloses all singularities of f? That is, if I have a bunch of singularities and like that, and then I have a contour that encloses every single singularity of f. Of course, then this contour is just going to be, again, the sum of all the residues. I can write that in that form. But again, this could be quite a few. What if there are a lot? Then there's a lot of work to be done there. And we know that this function then, what it means then, of course, is that everywhere outside of this contour, f is analytic. Okay, so one thing I can do, of course, is deform my contour so it's bigger and bigger and bigger. I can enclose more and more space inside this contour. And so it turns out that leads to a really nice perspective. So again, when C encloses all contours, we can kind of take a different perspective. And with we're going to consider then that the contour C encloses the point at infinity. So let's just take this perspective again. So again, I'm going to think about now our plane like so. I'm going to write the plane in 3D. I'm going to consider that compactification of the plane again. So let's say I have my finitely many singular points there. And again, I have this contour around it like that, and it's positively oriented. I'm going to just put the origin over there for now, just to make this easy. I'm going to do that compactification of the plane like I've done before. Like follows. And of course the North Pole that's my point at infinity. There's my infinity point. And the south pole of this ball is, of course, the origin, which is right there. And I've just drawn my singularities away from the origin, but that doesn't necessarily have a problem if I do have a singularity at the origin. All right, and the next thing I want to do then, of course, is I always like to think of this as there's an eyeball sitting there at the North Pole. And of course, if I'm looking at, I want to look at that projection of the plane onto this sphere, and of course, each point lies somewhere on that sphere, and of course the contour does as well, and so I can trace out that contour. And if I trace the contour out like that, what we can see is that the contour traces. So again, I can draw this sort of like this, right? And if I'm going this way on the contour, it projects backwards. So the contour, when projected onto our sphere, actually goes the opposite way. And so that's pretty interesting. See, as we go around, it goes the opposite direction. All right, so at least from looking from above, then, of course, so this is counterclockwise, and now the same contour on the sphere is going clockwise, right? But again, there's no singularities. F is analytic outside of here for all this region here, everywhere. This is all the singularities of the function. So of course I can make my contour a little bit bigger. I keep it counterclockwise. I can keep it bigger and bigger and bigger and bigger and bigger. I can keep making it bigger and bigger like that. Okay, so the question is, what does it happen? What this projection, when I go onto the sphere, of course, it does the same thing. It makes a bigger contour, and it makes a bigger contour. And eventually what it does, of course, is I start, if I keep making a bigger contour, it goes around like that. And it goes around the back side. And I can make it bigger and bigger and bigger until actually what I'm enclosing is infinity. So we see now that as continuous deformations of C to the further reaches of the plane is analogous to enclosing. I'm going to put that in quotes. The point at infinity. Okay. So the question then is, what do we mean by this? So that means then, if I have this contour, if I want to compute this integral f of z dz, of course I can use my formula 2 pi I times the sum of all the residues. Or what I'm now going to write down then, or I can write down this contour again as being the contour that's enclosing infinity of f of z dz equals 2 pi I times simply the residue at z equals infinity of f. Okay, so I'm begging the question here is like, what is that? How do I compute the residue at infinity? And we'll get to that into a second, but the idea is that we have this notion from thinking about that projection onto the sphere, this compactification of the complex plane into a sphere, that if there are no boundaries, if there are no singularities outside of my contour, there's no impediment from going further and further and further out. All right, so with this notion built in, then we now have the need to desire at will to define what a residue at infinity is. Okay, so let's do that. So let's think now in terms of, again, Laurent series. So again, we have this plane like there, and our singularities are sitting there, right? And we have this contour that's integrating and enclosing every single one of them. So one thing we can do then, of course, is as I make this contour bigger, like this, I can make it a little bit bigger like that. And eventually the contour can be sitting outside the radius of the last of our singularities. So I can draw a circle. I'm going to call that radius r. And my contour is totally embedded in that place beyond the radius r, beyond all the singular points, right? So I can expand a Laurent series. Oops. Of f at z equals 0, z naught equals 0, that converges for z greater than r. Okay, so of course we have from our previous results that this is a unique series. And the idea here is we're going to use is that if we want to look at that point at infinity, we want to take z to infinity. Or what we can do, of course, because we can look at 1 over z, where z is near 0. There's another way to do it. So if I then, of course, take the transformation z, and I'm going to replace z with 1 over z, then I have a way of talking about all of this region out here beyond, beyond all of our singularities. Okay, so that's the idea. So let's do that. So f of z then is going to be equal to this Laurent series. All right, and it's always a unique series, and we can always expand about the 0 point, but look at that unique series that converges only for that outer radius, okay? We're not looking for the series that converges on the inner radius or anything like that. So, of course, we can find such a Laurent series, or at least we can try to find it. But what I'm going to do then, of course, is I can write that out. And so, of course, what I want to find is that residue at infinity. So I want to find then, again, I don't know how to calculate these exactly, but what I do is I want to find c negative 1. Right. So of course that's going to be right here. What we have here is we have a c negative 2 times 1 over z squared plus c negative 1 over z plus c0 plus c1 times z plus z2, c2 times z squared, so on and so forth, and going backward in that direction too. So I want to find c1, c negative 1, sorry. So what I can do then is actually, now I'm going to do that transformation. I'm going to replace z with z 1 over z. Okay, right. So what I'll look then is for this one, f of 1 over z, and of course that becomes, I have my dot 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 there, I have a c negative 2, and that becomes then z squared, and so what I'm doing is basically putting a series in reverse, right? And then we have a c negative 1 times z to the first power plus c0, which always stays the same, plus c1, which becomes a 1 over z, plus a c2 over z squared, and it goes off that way. So I've sort of reversed the order of my my Laurent series here. Okay, the next thing I want to do is, again, if I take this whole thing and I multiply it by 1 over z squared, I'm going to do that here, 1 over z squared. What I get then is that I get that we have a c negative 2 here. Things going that way. And then we have a c negative 1, which is now, again, equivalent. We have a c negative 1 over z. So that looks just like our original series. That one term is equivalent. All the other terms are different, of course. Then we have a c0 over z squared. and then we have a c1 over z to the third power, and so on and so forth like that. Okay, so now what I'm looking at here then is, what I'm saying here is I can conclude that the residues of 1 over z squared f of 1 over z at z equals 0 is the same as f of z at z equals infinity. All right, and so what I can do then is then examine. I can use this as my tool for examining the residues. So if this isn't clear to you exactly how we're going to use this, it's going to be a lot more understandable when we so what we've done is basically take all these points out there far away from the origin, and we've mapped them to the origin, right? And all these points here, these singularities, they've been sort of just moved around a bit. But the point is then, now if I analyze the residue around 0 of this transformed function, then I have a concrete way of actually, I can put my contour around 0, I can integrate there and find my residue. So I can find this residue just fine. Okay. So the thing is this series here might be easier to compute. It might be easier to represent and to find its terms. So what I'll do is I'll illustrate that with a few examples. So we can do it multiple ways here. So let's talk about the example f of z is equal to 5z minus 2 all over z minus 1. All right, so this is a simple example. So first of all, and let's say again the goal is I want to integrate this contour of this function f of z dz, where the contour then encloses both 0 and 1. All right, so I've enclosed both these singularities, right? So what it's going to take then is I have to actually do. So I can do this the old-fashioned way, which is I've enclosed both my singularities because we have a singularity at 0 and a singularity at 1. Because of that, I can then go 2 pi I times the residue at one of them, which is we should be getting pretty good at finding these. It's going to be negative 1 over 5 times 0 minus 2 plus 1 times 5 times 1 minus 2. Okay, and if you do that, if you do this, you'll find out then, of course, that this is of course 2, and then it's going to be 5 minus 2. Add those together, and you get 2 pi I times 5. Okay, so that's how we can use the residue theorem to calculate this integral. And of course, there was 2 residues to do here. All right, so now let's use let's now transform. Because there's no boundary, of course, I can take my contour bigger and bigger. What I can do is essentially enclose infinity. So I'm going to try my other trick. I'm going to now analyze. So now I'm going to analyze 1 over z squared f of 1 over z, and I'm gonna look for the look at I should sorry, I'm gonna back off. I'm gonna erase this here for a second. Going to find the residue of z for this particular z at 0. Okay, so let's do that. So there's a 1 over z squared. Now everywhere I see in this function I see a z, I'm going to make it a 1 over z. So I have a 5, 1 over z minus 2 all over 1 over z times 1 over z minus 1. Okay, so there are many ways to do this, but let's see if we can sort this out. What I see right here is that if I factor out in the numerator a 1 over z, I have a 1 over z then, and that becomes a 5 minus z times 2, okay? And then I have a 1 over z in the denominator as well, times 1 over z minus 1, okay? All right, and then multiplied by the whole thing there was that 1 over z squared. Okay, so these cancel with one another. And then I see that if I take, I'm actually going to turn that into 1 over z times 1 over z. Okay? In which case, sorry, that's a 1 over z down there. I'm going to multiply one of those z's inside. So again, on the top I have 5 minus 2z all over, now what I have is a 1 minus z, okay, times, and then this final one comes in, that becomes a z. Right, now I'm going to look at this one and find its residue. And so there's two different ways to think about this. One is to think about, I want to look at its singularities, right? We see here it does in fact have a singularity at the origin, right? So again, I'm analyzing the residue at the origin now, not at infinity. So all I'm doing is enclosing the point at 0, which of course, because I've done that mapping, that's the same thing as analyzing the point at infinity of the original function. Okay, so I can look at that and I see that there is a singularity. There is a first power there. So there is, of course, 1 is another singularity, but I don't worry about that because I'm not enclosing it. I'm only enclosing this 1 here. Okay, so what I can do then, of course, is just compute the residue there using the old-fashioned technique of now going 5 minus 2z all over 1 minus z, all divided by z. Okay. So that, of course, this part of the function is analytic, and I can use the Cauchy integral formula to find out that's equal to 2 pi I. And then I can just evaluate at 0. So that's going to be 5 minus 2 times 0 all over 1. And, of course, that gets us the same result as we had before, 2 pi I times 5. Okay, so and then there's another way to do this as well, which is to, it's a little bit more nuanced, but and it takes a little bit more cleverness, but I can do that as well. So, sorry, what I have here is I have to just remember this. Okay, we have 5 minus 2z. Okay, good. Oops. So we have a our 1 over z squared f of 1 over z is equal to 5 minus 2z all over z times 1 minus z. Okay, I can rewrite this as 5 minus 2z all over z times 1 over 1 minus z. Okay, so what I see here then is I can rewrite this as actually a 5 minus z minus 2, put that like that, and then a 1 over 1 minus z. Okay. All right, and so this, of course, we're looking for z near 0. Okay. In which case, I know I have a convergence power series, which is also the Laurent series for this part of it, right? So what I have is a 5 minus z minus 2, and I can write that as n equals 0 to infinity of z to the n. Okay, and then the next thing I have to do is just multiply these in. And I see there's a 5 over z times the sum z to the n equals 0 to infinity. And then also a minus 2 sum n equals 0 to infinity of z n. And what I'm looking for, of course, is the what the coefficient is for the 1 over z term, right? That's what I'm looking for here. So I'm just seeing if I can pick it out of the lineup, so to speak, okay? And so clearly we can see that that is equal to, so when n equals 0, this is equal to, this is just 1. And so we see there's a 5 over z to the first power. And then, of course, when n is equal to 1, we get a plus 5, right? That would be that constant term. And then it's also a minus 2 because there's this part here. Okay, and then also then it would be plus, and then there'd be more going on here. This would be a 5 minus 2 z to the first power, and so on and so forth. But I don't care about any of those. I just care about this. That was the 5. That was the residue of 1 over z, f of 1 over z times 1 over z squared at z is equal to 0. That's going to be 5. So of course, just like before, we find that the result is integral around the contour of f of z dz, where we enclose all of our singularities, is again 2 pi I times 5. Okay, so now I hope you see how you can use this. And the idea here is that if you have, and so again, I should just put up here, I should say, if you have some function that's where the sum of all the singularity, I should put it this way, where all the singularities zk is a large set, and the contour C encloses all of them. Consider computing the residue at 0 of 1 over z squared f of z, 1 over z, sorry, instead. Because here, this is just only one residue. Whereas in general, if I didn't look at the residue at infinity, I have to go 2 pi I times the sum of k equals 1 all the way to n, where that's our n there, of the residues at zk for f. This could be, a lot of work. Okay. So if this sum is a very large sum, if there's quite a few of these to do, it might be better to only have to do one of them. So that's where really this theorem comes into play. So thank you very much.